All right, trigonometric form of complex numbers. Why is this coming up here when we're talking about exponents? Well, let's see if we can make some sense. We're also talking about roots, and that's the biggest reason. Complex numbers can be expressed in the standard form of a plus bi. The real part is a, the imaginary part is the bi, right? So b's still real, it's that extra piece. The complex numbers can also be expressed in trigonometric form, which uses r and theta to locate a complex number. So a plus bi is equivalent to r cosine of theta plus I sine of theta, where I is the hypotenuse, the radius, right? The radius of our, not unit in this case, but unit circle, where we are in whatever type circle it is. And so this is how they're related. A is equal to r cosine of theta. B is r sine of theta. So this relationship works. And we use this often when we're using to find roots. So de Moivre's theorem, let z be a complex number equal to r cosine of theta plus I sine of theta, and n be a positive integer. Then z to the n is equal to r to the n times the quantity of cosine n theta plus I sine n theta. This theorem can be used to find roots of complex numbers. So that's kind of the idea here. So z is a complex number. We're looking at non-zero complex number, and n is any positive integer, then this is true, and this has exactly n distinct nth roots. So the nth root of our radius times cosine of theta plus 360 degrees times k. Which one we're looking at? K is 0, 1, 2, up to n minus 1, plus I sine 0 plus 360 times k, and all this is divided by n. So if radian measure is used, then we would add the 2 pi versus 360, right? And here we're using, come on, the multiplication symbol. Here we're just putting them together, but 360 is equal to 2 pi. So this is a way to do it. If we had to find the following roots and express them in standard form, we could check the results with a calculator, though oddly with most of your guys' calculators, they're just going to approximate. So the cube roots of 216, cosine 180, plus I sine 180. So here they all are. I do the square root, or the cube root of 216. For this 0th one, it's just going to be cosine of, these would be my k's, right? Those are my k's. So 180 over 3, because it's the cube root. And then I sine 180 over 3. So I'm going to get 6 cube root of 216, 6 times 6 times 6. Cosine of 60 plus I sine of 60. That's at my 0. My 0th root at my first root. I have cosine of 180. This would be 1 times 360, right? 1 times 360. Well, 1 times 360 is 360. So 180 divided by 3 is 60. 360 divided by 3 is 120. So 60 and 120 is 180. So that's how we get this one. And then we have our 2, our second root. Again, this becomes 2, right here, that becomes 2. And at that point, I'm really taking that 120 and doubling it, so 240, plus my initial 60 is how I get 300. And that was just me doing it very quickly in my head. So here they are again. These are the 3 roots. We can then use our unit circle knowledge, and we know that cosine of 60 is a half, sine of 60 is the square root of 3 over 2. Cosine of 180 is -1, cosine of 100, or sine 180 is 0. And then hopefully you know your unit circles. You guys created your most creative. So cosine of 300 is a half, and sine of 300 is negative square root of 3 over 2. So then in standard form, this first one becomes this, which becomes this, which then becomes this, right? And I just plug it in, do the multiplication, and then the second one becomes this, and then becomes this, which then becomes this. And the third one goes to here, then goes down to here, and then goes over to here. You'll notice we get conjugate pairs. It should not be surprising. This should feel natural. There's our conjugate pairs. There, conjugate pairs, yep. Here and here. And then this one comes out to just be a number because there was only 3 roots. Okay. All right. We're going to do the real roots, the next piece separately, real exponents. All right. Have a good day.